We can label our GLN, UN or SUN irreps using Young diagrams, but that's not true for ON or SON irreps, at least in general. Sometimes the irreps labeled by the Young diagrams lead to representations of these orthogonal groups that are reducible. So here's an example. Consider the tensor product of the defining representation with itself, and we know that we get the symmetric two-index tensors and the antisymmetric two-index tensors here. And now this here, the symmetric two-index tensors, they are the representation carried by this subspace here that's reducible. So we can explicitly construct an invariant subspace of this thing here. To this end, consider this object, choose some basis here in the defining representation, and we label the basis vectors 1, 2, 3, 4, and so on. And now we take J tensor J and sum over all J's. And I claim that this spans a one-dimensional subspace of the space which carries this representation here. And by the way, this has dimension n times n plus 1 half. So we find a one-dimensional invariant subspace in here. And how do we find this? Just act with a orthogonal matrix G on this. So that was G in each factor. So what we really get here is some tensor product, let's say K tensor L. And now we have to sum over J as before, K and L, that's new. And here we get matrix elements, let's say G, K, J, G, L, J. But now G, L, J, that's just, maybe some other color here, that's just a matrix element of the transposed matrix. But then we have to swap the indices. So it's G transposed index J, sorry, not K, J, L. But the nice thing is that now the J sum, now if we look at it like this here, this is really a matrix product now. So we can say the J sum gives us the product of G times G transpose. But it's an orthogonal matrix, so we get a unit matrix. That is, the matrix elements are just a Kronecker delta. So we have tensor product KL, and now it's delta KL here. This means we can throw away one sum. Let's say we keep K, sum K tensor K, and we see that the thing is really invariant under these orthogonal matrices.